The 8086 is a 16-bit microprocessor chip designed by Intel between early 1976 and mid-1978, when it was released. The Intel 8088, released in 1979, was a slightly modified chip with an external 8-bit data bus, and is notable as the processor used in the original IBM PC design, including the widespread version called IBM PC XT. The 8086 gave rise to the x86 architecture, which eventually turned out as Intel's most successful line of processors. History, background. In 1972, Intel launched the 8008, the first 8-bit microprocessor. It implemented an instruction set designed by Data Point Corporation with programmable CRT terminals in mind, that also proved to be fairly general purpose. The device needed several additional ICs to produce a functional computer, in part due to it being packaged in a small 18-pin memory package, which ruled out the use of a separate address bus. 2 years later, Intel launched the 8080, employing the new 40-pin DIL packages originally developed for calculator ICs to enable a separate address bus. It had an extended instruction set that was source-compatible with the 8008 and also included some 16-bit instructions to make programming easier. The 8080 device, often described as the first truly useful microprocessor, was eventually replaced by the depletion load-based 8085, which could cope with a single 5V power supply instead of the 3 different operating voltages of earlier chips. Other well-known 8-bit microprocessors that emerged during these years were Motorola 6800, General Instrument PIC-16X, MOS Technology 6502, Zilog Z80, and Motorola 6809. The first x86 design. The 8086 project started in May 1976 and was originally intended as a temporary substitute for the ambitious and delayed iAPX 432 project. It was an attempt to draw attention from the less delayed 16 and 32-bit processors of other manufacturers and at the same time to counter the threat from the Zilog Z80, which became very successful. Both the architecture and the physical chip were therefore developed rather quickly by a small group of people, and using the same basic microarchitecture elements and physical implementation techniques as employed for the slightly older 8085. Marketed as source-compatible, the 8086 was designed to allow assembly language for the 8008, 8080, or 8085 to be automatically converted into equivalent 8086 source code, with little or no hand editing. The programming model and instruction set was based on the 8080 in order to make this possible. However, the 8086 design was expanded to support full 16-bit processing, instead of the fairly basic 16-bit capabilities of the 8080/8085. New kinds of instructions were added as well. Full support for signed integers, base plus offset addressing, and self-repeating operations were akin to the Z80 design but were all made slightly more general in the 8086. Instructions directly supporting nested ALGOL family languages such as Pascal and PLM were also added. According to principal architect Stephen P. Morse, this was a result of a more software-centric approach than in the design of earlier Intel processors. Other enhancements included microcoded multiply and divide instructions and a bus structure better adapted to future co-processors and multiprocessor systems. The first revision of the instruction set and high-level architecture was ready after about 3 months, and as almost no CAD tools were used, 4 engineers and 12 layout people were simultaneously working on the chip. The 8086 took a little more than 2 years from idea to working product, which was considered rather fast for a complex design in 1976–1978. The 8086 was sequenced using a mixture of random logic and microcode and was implemented using depletion load NMOS circuitry with approximately 20,000 active transistors. It was soon moved to a new refined NMOS manufacturing process called HMOS that Intel originally developed for manufacturing of fast static RAM products. This was followed by HMOS-E, HMOS-II versions, and, eventually, a fully static CMOS version for battery-powered devices, manufactured using Intel's CHMOS processors. The original chip measured 33 ms² and minimum feature size was 3.2 AI 1/4 m. The architecture was defined by Stephen P. Morse with some help and assistance by Bruce Ravenel in refining the final revisions. Logic designer Jim McKevitt and John Bayliss were the lead engineers of the hardware-level development team and William Pullman the manager for the project. The legacy of the 8086 is enduring in the basic instruction set of today's personal computers and servers. The 8086 also lent its last two digits to later extended versions of the design, such as the Intel 286 and the Intel 386, all of which eventually became known as the x86 family. Details: buses and operation, all internal registers, as well as internal and external data buses, were 16 bits wide, firmly establishing the 16-bit microprocessor identity of the 8086. A 20-bit external address bus gave a 1 MB physical address space. This address space was addressed by means of internal segmentation. The data bus was multiplexed with the address bus in order to fit a standard 40-pin dual inline package. 16-bit I/O addresses meant 64 KB of separate I/O space. The maximum linear address space was limited to 64 KB, simply because internal registers were only 16 bits wide. Programming over 64 KB boundaries involved adjusting segment registers and remained so until the 80386 introduced wide-domain registers. Some of the control pins, which carry essential signals for all external operations, had more than one function depending upon whether the device was operated in min or max mode. The former was intended for small single-processor systems while the latter was for medium or large systems, using more than one processor. Registers and instructions: the 8086 has 8 more or less general 16-bit registers. 4 of them, AX, BX, CX, DX, could also be accessed as twice as many 8-bit registers while the other 4, BP, C, D, SP, were 16-bit only. Due to a compact encoding inspired by 8-bit processors, most instructions were one-address or two-address operations, which means that the result was stored in one of the operands. At most, one of the operands could be in memory, but this memory operand could also be the destination, while the other operand, the source, could be either register or immediate. A single memory location could also often be used as both source and destination, which, among other factors, further contributed to a code density comparable to most 8-bit machines. Although the degree of generality of most registers were much greater than in the 8080 or 8085, it was still fairly low compared to the typical contemporary minicomputer, and registers were also sometimes used implicitly by instructions. While perfectly sensible for the assembly programmer, this made register allocation for compilers more complicated compared to more regular 16 and 32-bit processors such as the PDP-11, VAX, 68000, 32016 etc. On the other hand, it was more regular and orthogonal than ubiquitous but rather minimalistic 8-bit microprocessors such as the 6502, 6800, 6809, 8085, MCS48, 8051 and other contemporary accumulator-based machines. It was significantly easier to construct an efficient code generator for the 8086 design. Another factor for this was that the 8086 also introduced some new instructions to better support stack-based high-level programming languages such as Pascal and PLM. Some of the more useful ones were push memop and retsize, supporting the Pascal calling convention directly. The 8086 had a 64 KB of 8-bit I/O space. A 64 KB stack growing towards lower addresses is supported in hardware. 2-byte words are pushed to the stack and a stack top is pointed to by SS, SP. There are 256 interrupts, which can be invoked by both hardware and software. The interrupts can cascade, using the stack to store the return addresses. Flags: 8086 has a 16-bit flags register. 9 of these condition code flags are active, and indicate the current state of the processor: carry flag, parity flag, auxiliary carry flag, zero flag, sign flag, trap flag, interrupt flag, direction flag, and overflow flag. Segmentation. There are also 4 16-bit segment registers that allow the 8086 CPU to access 1 MB of memory in an unusual way. Rather than concatenating the segment register with the address register, as in most processors whose address space exceeded their register size, the 8086 shifts the 16-bit segment only 4 bits left before adding it to the 16-bit offset, therefore producing a 20-bit external address from the 32-bit segment offset pair. As a result, each external address can be referred to by 212 equals 4096 different segment offset pairs. The 16-byte separation between segment bases is called a paragraph. Although considered complicated and cumbersome by many programmers, this scheme also has advantages. A small program can be loaded starting at a fixed offset in its own segment, avoiding the need for relocation, with at most 15 bytes of alignment waste. Compilers for the 8086 family commonly support 2 types of pointer, near and far. Near pointers are 16-bit offsets implicitly associated with the program's code or data segment and so can be used only within parts of a program small enough to fit in one segment. Far pointers are 32-bit segment offset pairs resolving to 20-bit external addresses. Some compilers also support huge pointers, which are like far pointers except that pointer arithmetic on a huge pointer treats it as a linear 20-bit pointer, while pointer arithmetic on a far pointer wraps around within its 16-bit offset without touching the segment part of the address. To avoid the need to specify near and far in numerous pointers, data structures, and functions, compilers also support memory models, which specify default pointer sizes. The tiny, small, compact, medium, large, and huge models cover practical combinations of near, far, and huge pointers for code and data. The tiny model means that code and data are shared in a single segment, just as in most 8-bit based processors, and can be used to build COM files for instance. Pre-compiled libraries often came in several versions compiled for different memory models. According to Morse et al., the designers actually contemplated using an 8-bit shift, in order to create a 16 MB physical address space. However, as this would have forced segments to begin on 256-byte boundaries, and 1 MB was considered very large for a microprocessor around 1976, the idea was dismissed. Also, there were not enough pins available on a low-cost 40-pin package for the additional 4 address bus pins. In principle, the address space of the x86 series could have been extended in later processors by increasing the shift value, as long as applications obtained their segments from the operating system and did not make assumptions about the equivalence of different segment offset pairs. In practice, the use of huge pointers and similar mechanisms was widespread, and the flat 32-bit addressing made possible with the 32-bit offset registers in the 80386 eventually extended the limited addressing range in a more general way. Porting older software, small programs could ignore the segmentation and just use plain 16-bit addressing. This allowed 8-bit software to be quite easily ported to the 8086. The authors of MS-DOS took advantage of this by providing an application programming interface very similar to CP/M as well as including the simple COM executable file format, identical to CP/M. This was important when the 8086 and MS-DOS were new, because it allowed many existing CP/M applications to be quickly made available, greatly easing acceptance of the new platform. Example code: the following 8086/8088 assembler source code is for a subroutine named MEMCPY that copies a block of data bytes of a given size from one location to another. The data block is copied 1 byte at a time, and the data movement and looping logic utilizes 16-bit operations. The code above uses the BP register to establish a call frame, an area on the stack that contains all of the parameters and local variables for the execution of the subroutine. This kind of calling convention supports reentrant and recursive code, and has been used by most ALGOL-like languages since the late 1950s. The ES segment register is saved on the stack and replaced with the value of the DS segment register, so that the move AL instructions will operate within the same source and destination data segment. Before returning, The subroutine restores the previous value of the ES register. Performance. Although partly shadowed by other design choices in this particular chip, the multiplexed address and data buses limited performance slightly. Transfers of 16-bit or 8-bit quantities were done in a 4-clock memory access cycle, which was faster on 16-bit, although slower on 8-bit quantities, compared to many contemporary 8-bit based CPUs. As instructions varied from 1 to 6 bytes, fetch and execution were made concurrent and decoupled into separate units. The bus interface unit fed the instruction stream to the execution unit through a 6-byte prefetch queue, speeding up operations on registers intermediates, while memory operations unfortunately became slower. However, the full 16-bit architecture with a full-width ALU meant that 16-bit arithmetic instructions could now be performed with a single ALU cycle, speeding up such instructions considerably. Combined with orthogonalizations of operations versus operand types and addressing modes, as well as other enhancements, this made the performance gain over the 8080 or 8085 fairly significant, despite cases where the older chips may be faster. EA equals time to compute effective address, ranging from 5 to 12 cycles. Timings are best case, depending on prefetch status, instruction alignment, and other factors. As can be seen from these tables, operations on registers intermediates were fast, while memory operand instructions and jumps were quite slow. Jumps took more cycles than on the simple 8080 and 8085, and the 8088 was additionally hampered by its narrower bus. The reasons why most memory-related instructions were slow were threefold. Loosely coupled fetch and execution units are efficient for instruction prefetch, but not for jumps and random data access. No dedicated address calculation adder was afforded. The microcode routines had to use the main ALU for this. The address and data buses were multiplexed, forcing a slightly longer bus cycle than in typical contemporary 8-bit processors. However, memory access performance was drastically enhanced with Intel's next-generation chips. The 80186 and 80286 both had dedicated address calculation hardware, saving many cycles, and the 80286 also had separate address and data buses. Floating point, the 8086/8088 could be connected to a mathematical coprocessor to add hardware microcode-based floating point performance. The Intel 8087 was the standard math coprocessor for the 8086 and 8088, operating on 80-bit numbers. Manufacturers like Cyrix and Witek eventually came up with high-performance floating-point coprocessors that competed with the 8087 as well as with the subsequent, higher-performing Intel 80387. Chip versions, the clock frequency was originally limited to 5 MHz, but the last versions in HMOS were specified for 10 MHz. HMOS III and CMOS versions were manufactured for a long time for embedded systems, although its successor, the 80186/80188, has been more popular for embedded use. The 80C86, the CMOS version of the 8086, was used in the GRID-PAD, Toshiba T1200, HP 110, and finally the 1998 to 1999 Lunar Prospector. Derivatives and clones. Compatible EA-Euro, and, in many cases, enhanced CEDA-Euro versions were manufactured by Fujitsu, Harris Intersal, OKI, Siemens AG, Texas Instruments, NEC, Mitsubishi, AMD. For example, the NEC V20 and NEC V30 pair were hardware compatible with the 8088 and 8086 even though NEC made original Intel clones i1 Quarter PD8088D and i1 Quarter PD8086D, respectively, but incorporated the instruction set of the 80186 along with some of the 80186 speed enhancements, providing a drop-in capability to upgrade both instruction set and processing speed without manufacturers having to modify their designs. Such relatively simple and low-power 8086 compatible processors and CMOS are still used in embedded systems. The electronics industry of the Soviet Union was able to replicate the AT-86 through both industrial espionage and reverse engineering. The resulting chip, K1810BM86, was binary and pin-compatible with the AT-86. iAT-88 and iAT-86 were respectively the cause of the Soviet-made PC-compatible EC1831 and EC1832 desktops. However, EC1832 computer had significant hardware differences from its authentic prototype, and the data address bus circuitry was designed independently of Intel products. EC1832 was the first PC-compatible computer with dynamic bus sizing. Later some of the ES1832 principles were adopted in PS/2 and some other machines. Hardware modes. The AT-86 and AT-88 support two hardware modes, maximum mode and minimum mode. Maximum mode is for large applications such as multiprocessing and is also required to support the AT-87 coprocessor. The mode is usually hardwired into the circuit and cannot be changed by software. Specifically, pin number 33 is either wired to voltage or to ground to determine the mode. Changing the state of pin number 33 changes the function of certain other pins, most of which have to do with how the CPU handles the bus. The IBM PC and PC XT use an Intel AT-88 running in maximum mode, which allows the CPU to work with an optional AT-87 coprocessor installed in the math coprocessor socket on the PC or PC XT mainboard. Peripherals, Intel 8237, Direct Memory Access Controller, Intel 8251, USART, Intel 8253, Programmable Interval Timer, Intel 8255, Programmable Peripheral Interface, Intel 8259, Programmable Interrupt Controller, Intel 8279, Keyboard Display Controller, Intel 8282/8283, 8-bit latch, Intel 8284, Clock Generator, Intel 8286/8287, Bidirectional 8-bit Driver, Intel 8288, Bus Controller, Intel 8289, Bus Arbiter, microcomputers using the AT-86. The Xerox note-taker was one of the earliest portable computer designs in 1978 and used 3 AT-86 chips, but never entered commercial production. Seattle Computer Products shipped S100 bus-based AT-86 systems as early as November 1979. The Norwegian Micron 2000, introduced in 1980. One of the most influential microcomputers of all, the IBM PC, used the Intel AT-88, a version of the AT-86 with an 8-bit data bus. The first compact desk Pro used an AT-86 running at 7.14 MHz, but was capable of running add-in cards designed for the 4.77 MHz IBM PC XT. An 8 MHz AT-86 was used in the AT&T 6300 PC, an IBM PC-compatible desktop microcomputer. The M24/PC 6300 has IBM PC XT-compatible 8-bit expansion slots, but some of them have a proprietary extension providing the full 16-bit data bus of the AT-86 CPU. The IBM PS/2 models 25 and 30 were built with an 8 MHz AT-86. The Amstrad Schneider PC 1512, PC 1640, PC 2086, PC 3086 and PC 5086 all used AT-86 CPUs at 8 MHz. The NEC PC 9801. The Tandy 1000 SL series and RL machines used AT-86 CPUs. The IBM Display Writer word processing machine and the Wang Professional Computer, manufactured by Wang Laboratories, also used the AT-86. NASA used original AT-86 CPUs on equipment for ground-based maintenance of the Space Shuttle Discovery until the end of the Space Shuttle program in 2011. This decision was made to prevent software regression that might result from upgrading or from switching to imperfect clones. KAMAN process and area radiation monitors, notes. See also, iAPX, for the iAPX name, references. External links. Architecture of AT-86 and pin at scanfdre.com, Intel datasheets, List of 8086 CPUs and their clones at cpuworld.com. 8086 pinouts, maximum mode interface. The 8086 uses manual. October 1979 Intel Corporation. 8086 program codes using EMU. 8086 emulator. Intel 8086/80186 emulator written in C. This file is part of a larger PC emulator.